We are rocking and rolling, everybody. Okay, so let's get started. We are on lecture 35. We only have 43 lectures left in the whole semester, so we're definitely on the near the end. Seventh inning, final quarter, whatever analogy you want to use. We're down to the wire. So a couple housekeeping items. How did that beam analysis assignment go where you had the zone 2 and zone 3? Was that? I'm hoping it was pretty straightforward. Again, the primary purpose of it was just to make sure you're comfortable with the expressions. We are going to use them quite a bit. I will say that I mentioned it before, but I'll mention it again, that if in design land, which we're going to enter design land today, the one zone you should be most comfortable with in design mode is zone 2. Okay, zone 2 tends to be what governs design. Now, I don't know that anybody or any of, I guess, my peers who teach structural steel design present beam design this way. Maybe they do, maybe they don't. But this is how I've chosen to present discretely braced beam design. And what I do is I sort of do it in two parts. And what I do is I call it low CB design and then high CB design. And that'll make sense when we start getting into the examples and how we handle it. But there's something that happens in design mode whenever you have a really large CB value. There's a little bit more iteration that needs to happen. And I don't want to spoil things, but what I'll say is there's a lot of page flipping. You'll go here, then go here, then go here, then go here. And so I just want to prepare you for that because that's going to happen. So, but we'll get to that here today. Everybody get the code? All right. Okay, so let's open up our notes and sort of see where we're at. Okay. All right, so just to make sure we're all on the same page, I'm hoping by now we're comfortable with this flowchart. The idea that the first thing that you want to do if you want to assess a beam's capacity is determine what zone you're in. And one of the things that's interesting, I didn't say if you want to determine a discretely braced beam's capacity. This flowchart, by the way, works for a continuously braced beam as well. Why does it work for a continuously braced beam? Well, if it's continuously braced, what's LB? 0. And 0's got to be less than this, right? So you're in zone 1, so that's your capacity, right? So that's this flowchart works for continuously braced beams, discretely braced beams, doesn't matter, okay? So if you're in zone 1, you're in full plastic moment land. If you're in zone 2, you're in inelastic buckling. Zone 3, you're in elastic buckling. Zones 2 and 3 both have a cutoff of MP. So both of the capacities are the minimum of some computed expression and phi MP because that's your cutoff. Again, CB serves to augment your flexural capacity, but it can't augment the flexural capacity past what we statutorily define as the maximum capacity that a beam can withstand, which is phi MP. Zone 2 is basically linear interpolation, where that BF term is the slope of the line between phi MP and phi MR. And then zone 3 is this. Is it difficult? No. Is it a long calculation? Yeah, I can't really get around that. It just is what it is. Okay. Sound good? All right. So table 310. We talked about this last time, but this is our design aid for LTB capacity for designing according to LTB. So again, what we would do is if we are given, let's say, an unbraced length and a moment, the first thing we do is we divide out the effects of CB. So we take that maximum moment and we divide the value of CB to get some value. And then we'll go on the x-axis with this, the y-axis with that, find that point in the chart, and then we say everything up here is safe, right? Because everything up there corresponds to sections that have larger moment capacities and longer LB distances. So anything up and to the right will work, and what we'll do is find the first solid line, and that's going to be our trial section. And remember, we go with the solid line because in that range, that's the lightest section. It's sort of like the bold row in table 3.2. Remember in table 3.2, the sections were organized in chunks, but the bold row was the one that we used because it's the lightest. Same thing here. Okay? So let's talk about designing discretely braced beams. Let's see if we can develop a process. Okay? So this process is going to be very much like the process for a continuously braced beam. So the first thing that we're going to need to do is our structural analysis. So we're going to need to compute our maximum factored moment. But this is a little different than, not really different, but it's maybe a little bit more comprehensive than what we did for continuously braced beam design. Because for continuously braced beam design, we never worried about CB. Right? It didn't matter. And even in our flowchart, CB doesn't affect zone 1 capacity at all, right? So if we're in continuously braced beam land, we don't care about CB. But now that we're in discretely braced beam land, we need that too. And I would argue CB is more of a structural analysis phenomenon. Like that's what it is. So what we need to do is we need to, when we're doing our structural analysis, get our maximum factored moment. I guess I should put up here the maximum factored shear too, although up until now we've realized that shear hasn't really affected beam selection, so we do it, but not really that big of a deal. And then we need to get our associated CB value, okay? Hopefully we can use table 3.1 for CB, so we don't have to calculate CB. Hopefully we can just look it up. And we should assume a beam self-weight somewhere between 50 or 100 pounds per foot. I guess the only time that you should not assume a beam self-weight is if you're told in the problem statement something along the lines of, here's some dead load, and by the way, that includes the self-weight. If that's the case, then don't worry about it, okay? This is still a beam design problem. This hasn't changed, right? Remember, the only difference between a continuously braced beam and a discretely braced beam is the moment capacity. We do still have shears to meet and deflections to meet as well. So we still need to compute our required moment of inertia based off deflection limits, and that doesn't change. It's the same thing we did before as what we would do here, okay? So after step 2, see, when we were doing continuously braced beams, we sort of arrived at these two terms, but now we're going to have MU, our moment of inertia, but then we're also going to have CB. We're going to have to incorporate that in our design philosophy as well. Okay, so what do? Okay, so now what we do is we go to table 310 and we select the most economical section. So those are the beam charts. And what do? We go into table 310 with this on the x-axis and this on the y. So we take MU and we divide out our CB term. Okay, and we get a trial shape. Now if we look at that trial shape and we find the trial shape has a much smaller moment of inertia than what we need, we go to table 3.3 and we look up the section. So that didn't change either. And you can skip this step if that isn't the case. If you find that your moment of inertia is more than adequate, then just skip step 4 and go on to analysis land. Okay, and as for analysis land, what do we need to do? We need to analyze moments, shears, and deflections. Now, I do want to say one note on moment capacity here, and that is that if I'm being honest, okay, so let's go back to continuously braced beam design because I want to have a thought experiment. Okay, so let's assume that you're designing a beam. Okay, let's assume you're designing a beam, and let's say it's a continuously braced beam. So let's ignore all this buckling stuff. Okay, and let's say that you assume a self-weight of 100 pounds per foot, okay? Let's just say you assumed that, okay? And then after you did a bunch of math, you found that a W24 by 76 would be a viable candidate. Did you need to check the moment capacity? Did you need to go back and actually check its moment capacity? You're shaking your head no. Why?
Because the actual self-weight of the beam is less than we assumed.
100% right. Okay. So if this was the case, that'd be different, right? You'd have to go and update your moments and whatnot. So I would argue for a continuously braced beam, this assessment of moment capacity was largely a formality, if I'm being honest. Especially if that's the case. In discretely braced beam land, absolutely not a formality, okay? And the reason why is because of what happens when you have high CB values, okay? And we're going to talk about this on Wednesday, but high CB values can generate what I'll call false positives with designs. And I've got an example on Wednesday that'll sort of illuminate that, and you'll kind of see what's going on. But I want to get used to the basic process of design first, so I'm restricting these examples to ones that are low CV values so that that false positive phenomenon won't happen. We'll get to that on Wednesday. Now, the only other thing I'll say in design mode is that, so let's say your chart kind of looks like this and the lines are really like vertical and whatnot. Sometimes it may be kind of easier to just trace upwards and find the shape. Sometimes this is easier, sometimes looking that way is easier. I will admit sometimes with some of these charts the lines can get a little crowded. Again, I think the best way of resolving that confusion is just more practice. So speaking of, let's do a problem. Okay, so we're going to do the following problem, and we're going to design a discretely braced beam as shown. Okay, so let me pull up the notebook here. This is going to be our goal for today. A little bit bigger. Okay, bless you. All right, so we have a discretely braced beam, okay, and I have given you a beam that is only braced at the ends, okay? It's not braced in the middle, it's not braced throughout. The only bracing that's provided is provided at the ends, okay? So what is LB for this beam?
24.
24 feet, okay. So the length and LB are in fact the same for this beam, okay? So there's that, okay. So we've got a beam simply supported, uniformly distributed dead load, uniformly distributed live load, okay? And what we're going to do is select a beam to safely resist these loads. Now the dead load I've given does not include the beam self-weight, so we're going to actually assume a somewhat heavy beam. We're going to assume 100 pounds per foot. I tend to do that when you have somewhat longer LBs. Like if the LB gets above like 20 feet, you'll probably see me want to assume like 100 pounds per foot. If it's under, I might go with 50. So that's just sort of my, like, what makes me, you know, warm and fuzzy when I'm in design mode. So anything in the 30s or higher, I might assume like 150 or something. I don't know. So, but in building design, not as common to have beams that long that don't have some degree of bracing. Okay. All right, so we're going to also ensure that this design has a live load deflection, or is limited to a live load deflection of L over 360, which is a very typical and standard limit for most routine design. So I would say this problem is about as real world as it gets. You know, this could be a beam in this building. Like, it really could be. So, all right, so let's get down to it. So let's do some structural analysis first. So what we need to do is determine some moments and shears for the beam. We also need to determine CB, which we'll talk about that here in a second. But let's write some stuff down. So So that's assumed. Okay. So this is our problem. You know, simply supported beam, uniformly distributed load, pretty straightforward. So let's see if we can chug out some responses here. And I'm hoping, by the way, that I can sort of, at this point I'm hoping that this is pretty straightforward. In other words, we don't need to be hyper formal with our substitutions. So we know that the dead load shear is going to be that, right? And we know that our dead load moment is going to be that. I mean, is that okay? Right? So this is going to be 1.1 times 24 over 2, so 1.1 times 12. That ends up being something like 13.2 kips. And this is going to be 79.2 foot kips. Do that. And then our live load shear. That ends up being 36 kips. Which is that. Is that okay that I'm doing this part kind of fast? I'm hoping by now we're sort of good with this. So what do I do with these, by the way? Just make sure we're all on the same page.
Put them in the factor.
There we go. We load factor. Okay. This one ends up being 73.44 kips. And this is 440.64 foot kips. Again, I'm hoping this is straightforward. We've been doing this enough by now that I think we can chug through that part pretty quickly. Okay. The other thing, okay, so this is the part that's like a little new, and that is our moment gradient modifier, which again, we're going to try and see if we can use table 3.1. Let me move this over a little bit. Okay, so let's just make sure we're clear on our problem. We have this. We have this. And we have that. So the beam is only braced at the ends. We derived this one, by the way, on one of our homework assignments. And one of the things that's kind of interesting is if you follow that derivation, I gave you that derivation for a specific span and a specific load. But if you were to replace the span with any number or the load with any number, the CB doesn't change. In fact, if you just use W and L, all the W's and L's cancel, and you would get a CB of what?
1.14.
Okay. All right. So just to make sure we've got a nice little record of what we've left step 1 with, I'm going to just write some stuff here on the board. So we know that VU is 73.44 kips, okay? And we know that MU is 440.64 foot kips. And we know that CB is 1.14. And so like I said, we're dealing with low CB terms right now. So, okay. All right, step 2 is going to be the same as we've done before. Step 2 is going to be looking at our required moment of inertia, okay? hold on. Let me take a step back. Does anybody need this? Y'all got this? Okay. You go away. I say go away. All right, so just to recap some of our parameters, we know that we know that. And what is E again? Okay, so, all right. So what we're going to do is we're going to look at our limit. Which for this problem was L over what? 360. And what am I forgetting? There we go. Okay. This one I'm going to do for you. Next one you all are going to do for me. All right, so this is 0.80 inches. Okay. All right. So our maximum deflection on the beam, if we have a simply supported beam subjected to a uniformly distributed load, we know that our maximum deflection, like what we're actually going to get on the beam, is that. And I notice I left a little space here because I need to incorporate that whole lovely 1728 conversion factor. Okay? So what we'll do, like we've done on numerous instances prior to this, is set this equal to 0.89, and we're going to solve for Ix. So all we're going to do is do a switcheroo, and therefore Ix required is going to be this over and then we're just going to replace the Ix with the limit, okay? So that's going to be 5 that 24 feet. Don't forget to raise that to the 4th power. Okay. Okay, this one, I'm going to make sure you all are awake this Monday morning. Tell me what you got for this one. 965. Okay, so after step 2, we know that the required moment of inertia is about 965 inches to the 4th. Okay, that's what we know. All right, everybody with me so far? Okay, so now for our design exercise. Okay, so can I scroll? Apparently I can't. There we go. Okay, now Remember, what do we go into the chart with? On the x-axis, we go into the chart with what? LB. And what was LB for this problem?
24 feet.
So LB is L, which is 24 feet. And what do we go in on the y-axis?
MU over CB.
Our moment, but we have to divide out the effects of CB. So we need to divide this out. So MU over CB is 440.64 foot kips over 1.14, which is what? I do want to make a point about this after we do this calc, by the way.
386.53.
Okay, second. Okay, I want everybody's eyes up here because this is important. Is this the moment that's on the beam? No. This is the moment that's on the beam. The only reason that we're doing this division is so that we can use table 310. So I want to be crystal clear. This is not what the beam has to withstand, okay? This is just an abstraction that we're doing so that we can go into this little table in the manual and look a section up. So I don't want you to, whenever you're calculating phi mn, to compare it to this. You don't compare phi mn to this. You compare phi mn to that. That's an incredibly important distinction, okay? Everybody with me on that? That's important. Okay. Now what I want everybody to do is I'm going to give everybody a second, but I want you to go into table 310. I want you to see if you can find me the lightest shape inside table 310 that meets those requirements. So an LB of 24, let's see if I can go through and do it on the screen here with you for a little bit, but an LB of 24 and an MU over CB of 386.53. All right, so let's see what I can do. So I decided to let me see if I can, there we go. So here's this. 386.53. Probably need to go one page over. This is about where we want to be. So is it's 20, 22, 24. Okay, so I'm on page 3-119. Okay, so this is 20, 22, 24, right? So if I go back to the page here, so see where it says like 20, 22, 24, so I'm using that third vertical line. And then we're using, what is it, 386.53, is that what we're using? So, increments of 3, 8, 81, probably something about like that. Is that sort of probably what we're looking for at that point right there? Okay, and so we'll say that anything this way is good. So that means that that's the shape that we're looking for, right? What shape is that?
W18 times 76.
W18 by 76. Okay. Now somebody help me out. Let's check one other thing. Okay, so let's look at step 4, okay? Yeah. let's check our IX required. Okay, what was IX required? It was 965. Okay, so help me out. What is IX for a W18 by 76? 1330. Okay. So is the W18 by 76 at least a viable candidate right now?
Yes.
Yeah, it is, right? It's gonna, the deflection requirement isn't really an issue. Okay. Sound good? And is everybody comfortable with this part, with the table 310, with finding the shape? You can see I'm going off the blue numbers, so we're about like right there. You know, here, there's the 24, so we go up. Sound good? Okay, and again, all this is just all those LTB curves all plotted on top of one another. And basically what they do is they go in and they say, okay, for a given region, whichever's the lightest, draw that with a solid line. So it's pretty straightforward. In fact, if you actually start following the chart, there's areas like this is kind of interesting where it goes, like here it goes solid, 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 and then it goes dash because it stops becoming the lightest section in that region. So it's kind of interesting. So, oh, I'm a dork. It's okay. All right, everybody good? Okay, so we've got a section that we think is sort of valid. Okay, so what I think is the most important thing that we do right now is check this section, okay? And I'll say this, if I'm being honest, for this problem, it's kind of a formality. But for Wednesday, especially when we have high CB values, 100% totally not a formality. This is really important. So we are going to go ahead and analyze the W18 by 76 just to develop good habits. Okay. All right. So a couple notes I'm going to make before I, jump into this, is that okay, so the beam is lighter than what we assumed. We assumed 100 pounds per foot, and we have an 18 by 76. So I'm just going to use the MU and the VU that we computed from before. So if it works, it works. Now, let's say that it doesn't work, but it just barely doesn't work. Like the performance ratio is 1.0001. Then I'll update the weights. But if it works, it's going to work. And I'm fairly comfortable that this is the lightest shape that I could find that would withstand these loads. So I'm just going to use the MU and the VU as previously computed. I know there's folks out there who say you might as well go ahead and update it. And I mean, if we were spreadsheeting these calculations, I would update it. But just doing it by hand, I'm not going to worry about it. Okay. All right. So how do we analyze a W18 by 76 to determine its flexural capacity? If I want to determine how much moment capacity that it has, what's the first thing I need to figure out?
Which zone it's in.
Which zone it's in. Okay, so let's do that first. Okay, so for a W18 by 76, okay, and I'm going to get this from table 3.2. Table 3.2 is one of the most useful guides in the steel manual, period. Okay, so how do I determine what zone it's in? What values do I need?
LP and LR.
LP and LR. Okay, what are LP and LR for a W18 by 76?
LP is 9.22.
And LR is
27.1.
Okay. And remind me, what was LB again? It was 24 feet. And so what zone does that put us in?
2.
I told you that in design mode, more often than not, when you're designing sections and you're selecting sections, when you go back and analyze it, it'll be in zone 2. That's probably the most common result you will find. Okay, so in order to do zone 2 capacity, okay, so let's literally look at the zone 2 equation. Give me some terms that I need for the zone 2 equation. Like I'll start us out. Do I need CB?
Yes.
Yeah, I need CB. Okay, what is CB?
1.14.
Okay, what's another term that I need in the zone 2 expression?
VBMPX.
I need the plastic moment capacity. So what is phi and P for a W18 by 76? 611. Okay, what's another term that I need?
VBBF.
I need phi BF. And that's the slope of that line in zone 2. And what is that?
12.8.
Okay, there's two other terms I'm going to need. I'm going to need LB, which is 24 feet. I'm also going to need LP, which is 9.22. I just want to have all those written down so they're right here. And so when I start plugging and chugging over here, you see where I've got them. Okay, so the first thing that I'm going to do is the top part of that moment expression. All right, and again, this expression looks really intimidating, but a lot of these terms sort of collapse because we've got 1.14, 611 minus 12.8 kips. And that gives us what?
480.87.
480.87. Second? Okay. So, PMN is the minimum of, and again, I'm lazy, so this is sort of how I write it. All that stuff we just did, so when I say CB times this bracket with the 3 dots, I'm just talking about all this, the minimum of all that, or phi and P. So this is the minimum of 480.87 or 611, and this is 480.87. Everybody okay with that? So just like to recap, okay, let's just do a nice little summary here at the bottom, okay? Let's start off with shear. What's the shear capacity for a W18 by 76?
252.
And what did we compare that against?
73.44.
73.44. Are we good here?
Yes.
Of course we are, yeah. And so our performance ratio for shear, if you divide these two out, you get something like 0.317. Like it's really tiny. Again, that happens with shear. Okay, moment. All right, we now have a moment capacity. And just so that we're all paying attention, what is that moment capacity?
480. Yeah, 480.87.
and I compare that against an MU, which is
440.64.
this, not that. Okay, this was just an analytical tool to be able to use the table. Once we got our section, ignore all this. We go back to this. So 440.64. Are we okay?
Yes.
Okay, and our performance ratio here, if we divide MU by FEMN, comes out to be like 0.916. And let's just make sure again we remember this. IX required was 965.3. And then the IX actual was, didn't we say 1330? So one thing you can do is if you want your performance ratio for deflection, you could compute the deflection and then take that deflection, divide it by 0.8, or you could just divide these two. It'll give you the same answer. So I'll just say this is okay. And our deflection performance ratio is something like 0.726. Okay. So now that we've done a bunch of math and a bunch of computations and a bunch of hullabaloo, what's the answer?
W1876.
W18 by 76. That's the answer. Use a W18 by 76. So what we just did is this beam in the building, we just said this is the beam we're going to use. This is the beam we're going to use to safely resist these loads. And if you can do it for this beam, you can do it for any beam in the building. Okay? Think about what we've done this semester. The beams, the columns, the connections, we're basically working towards the whole building. And just so everybody's aware, what we're going to do after we get done with beams is we're going to look at sort of the building as a whole. Things like, well, Dr. Mike, I see you got a beam that's 24 foot long with 3 kips per foot of live load. Where'd you come up with the 3 kips per foot? Where'd that come up from? So we're going to look at building applications to sort of tie everything together. So we're getting there too. Yes?
And if those don't work out, you just go back to the table 3 times and connect these?
Yes, and that's kind of what's going to happen with high CD values. It's not quite what's going to happen, but the answer to your question is yes. But let me put it like this. We're going to do that anyways with high CD values, so you'll see what I mean. All right. Before we end, well, first off, anybody have any more questions on this? Okay. Before we end, I want to say a couple words about the next homework because this is kind of important. Which folder do I have it in? I have it in this folder. Oh no, I have it in my other. Oh, I have it in my other flash drive. I'll have to post that real quick. Okay. So the only thing I'll say about that homework assignment is that homework assignment has, if it's the one I'm thinking of, it's got multiple unbraced lengths, but one of them clearly governs because it's got the longest LB, the smallest CB, and the biggest moment. So you can sort of ignore the ones on the ends. But I'll have that posted here in a little bit. Everybody good? All right, I'm going to pull the QR code one more time. If you did not get your exam, come on up and I'll give it to you. Otherwise, I will see you all on Wednesday.